We will now discuss two additional tools, powerful tools, that will help us in finding the real zeros of a polynomial function. The first one is simple but intuitive and very, very powerful. It says that a polynomial of degree n will have at most n real zeros. Another way of looking at this is saying that each zero gives us a factor. So for example, if we have a degree 4 polynomial, we'll do some examples here. We could have f of x equals x times x minus 5 times x plus 1 times x minus 2. So we can see that each of these factors gives us a 0, or vice versa, each 0 gives us one of these 4 factors. So this is an example of a degree 4 polynomial with 4 real zeros. But we could also have a degree 4 such as this, g of x equals x times x minus 5 times x plus 1 squared. It's still a degree 4, but since this factor is squared, we actually only have 3 real zeros. But if we wanted to try to make a degree 4 polynomial with 5 real zeros, that would be impossible, because then we'd have to have another linear factor, such as this, and we'd have to add another factor on there, which would make that no longer a degree 4. It would become a degree 5. So you can just think of it as, just ignore that, each 0 gives you a linear factor. So if r is a 0, x minus r is going to be that factor. So the degree tells us the maximum number of real zeros of a polynomial function. Very, very powerful. Another useful theorem is the rational zeros theorem. Okay, so let's first remember rational. When you hear rational, you want to think rational, fractional. They sort of rhyme. So this theorem is going to give us all the possible rational zeros. So that would include positive and negative whole numbers. So it will include integers and fractions. But it would not include, so let's note that, fractional would not include square roots that we can't simplify, such as the square root of 5, or irrational numbers like pi, etc. So this theorem is only talking about the possible rational zeros, the ones that can be written as a fraction. So if we want to determine the possible rational zeros of a polynomial function, and the function will have to have integer coefficients, but we won't trick you. We'll only use this when we're given polynomials with integer coefficients. We can find the possible rational zeros, and they will be in the form p divided by q, p over q, the fraction p over q, where p is a factor of the constant, and q is a factor of the leading coefficient. Okay, so let's just remember, this is only giving us possibilities. It's giving us a list of possibilities. It might turn out that none of those zeros on the list are actually zeros of that polynomial function. But it's a list of possibilities that can help narrow down our work once we start identifying zeros of these polynomials. So let's look at this example, example 3. So we're given this function, f of x equals negative 4x cubed plus x squared plus x plus 6. So part A, we want to determine the maximum number of real zeros of f. So all we need to do is look at the degree. So we have a degree 3 polynomial. So we know we have a maximum of 3 real zeros. Part B, we want to list the potential or possible rational zeros of f. So we need to list the p and the q. P is going to be factors of the constant. In this case, our constant is 6. So we want here for p, we want factors of 6. Now I'm going to put one plus or minus symbol out in the front so you don't have to write it in front of every number, because we know any of these factors could be positive or negative. So I'll just put one plus or minus sign in the middle, and then we just want to list all the factors of 6. So 1, 2, 3, 6. Then we want to list the Q values. Q is going to be factors of the leading coefficient, which in this case our leading coefficient is -4. So if you just want to write yourself a note, this is factors of -4. So again, you can put one plus or minus symbol in the front, meaning that any of the numbers in the list could be positive or negative. So our factors of 4, 1, 2, and 4. So the potential rational zeros are all the possibilities, all the possible combinations of p divided by q. So we're going to take each of these p values and divide by each of these q values. So we'll take the 1 over 1, 1 over 2, 1 over 4. So 1 over 1 is 1, 1 over 2 is 1/2, 1 over 4 is 1/4. Then we'll take the 2 over 1, 2 over 2, and 2 over 4. So 2 over 1 is 2. 2 over 2 is 1. We already have that. 2 over 4 is 1/2. We already have that. Now we'll take 3. 3 over 1, 3 over 2, 3 over 4. So 3 over 1 will give us 3. 3 over 2, 3/2. 3 over 4, 3/4. And then finally take the 6 over 1, 6 over 2, 6 over 4. So 6 over 1 will give us 6. 6 over 2 is 3. We already have that. And 6 over 4 is 3/2. We already have that. So this is a list of possibilities. It could turn out that none of these are actually real zeros of this polynomial, but this includes all the possible rational zeros. So that means, for instance, there's no way 7 could be a real zero of this polynomial function because it doesn't appear on this list.